The reaction of transesterification is actually very closely related to some other reactions. Transesterification is a reaction that will allow us, in a single reaction, to switch the R group on our ester. Typically, this reaction is done using whatever new alcohol we'd like to have as the R group, and then using an acid catalyst. And as a result, we can place a different R group on our ester. Now, the mechanism of this reaction is one that we're already likely to be very familiar with. Essentially, this reaction follows the exact same mechanism as the Fischer esterification. The only real difference between this transesterification reaction and the Fischer esterification is that for the transesterification, because we've already have an ester, our leaving group is going to be different. But outside of that, the mechanisms are basically identical. In order to illustrate that, I'll do the two mechanisms simultaneously. So here we're starting with a methyl ester. Down below, we'll start with the corresponding carboxylic acid. In both cases, we'll show the reactions with ethanol in acid. Both reactions have the same equilibrium concerns, and so just as we talked about with the Fischer esterification, in the case of the transesterification, we would also use an excess of the alcohol. So we start, because we're under acidic conditions, we don't have a strong nucleophile. Both reactions begin with protonation of the carbonyl, which activates it for nucleophilic attack. That step is immediately followed by nucleophilic attack of the alcohol. Which again we can see is the exact same reaction in either case. We then transfer the proton from the ethanol that just came in over to our leaving group. Same thing in our Fischer esterification. From here, our OH group adds its electrons back in, kicks out our leaving group, which in transesterification is going to be an alcohol of some sort, whereas in the Fischer esterification, that leaving group is just water. And that's actually going to leave us with the exact same intermediate for both reactions. It's a product with the protonated carbonyl. And so in order to complete the reaction, we just lose the proton that regenerates our acid catalyst. And gives us our new R group. So as you can see in this transesterification, we started with one R group on our ester, and we ended up with a different R group. Again, equilibrium controlled completely by our choice of adding excess alcohol, as we used in the Fischer esterification as well. Limitations on this reaction are pretty much the same as the Fischer esterification. We're using a strong acid here, often heating it as well. And so any functional groups that are sensitive to strongly acidic conditions, you're going to struggle being present with the Fischer esterification. One kind of interesting application of this, if we start out with a molecule like this, and these R groups can be any number of different long chains. Here is a triglyceride. And the triglyceride contains the three separate ester functionalities. That's what sort of holds the triglyceride together. It's the bond between glycerol and then the fatty acid. Well, if we undo that process using something like methanol or ethanol or propanol, and we'll show it with propanol here. Again, adding an abundance of that alcohol, we can actually break this apart. It's not a hydrolysis because we're not making carboxylic acids. It's still a transesterification. It's just now we've made three separate ester molecules instead of one ester where they're all put together. But you can see that just like on the previous page where we used a very much simpler example, here we've taken off this glycerol group and replaced it with whatever we added as an alcohol. Again, in this case, this is 1 propanol. And what have we made here? Well, these molecules over here are known as biodiesel. And biodiesel, you may be familiar with, is an alternative fuel source. And we can make it very easily. For those who are taking the course with me, in our Organic 2 lab, this is one of our experiments. We go, and in the past, we've been able to get used fryer oil down from the culinary school, and we take that and we mix it with methanol, ethanol, or propanol under acidic conditions, and we form biodiesel. And as part of that experiment, you may get to test that biodiesel to see how it compares to the original vegetable oil, both in terms of its viscosity as well as its flammability.